Hi everyone, so in this video we're going to be talking about logarithms. This is kind of an introduction to logarithms, what they are, kind of the basic properties. By the way, logarithms have nothing to do with logs or rhythms. It comes from a couple Greek words that basically means proportion and number. And kind of in their basic form, all logarithms are is it's a way to undo exponentials. It's a way for us to solve exponential equations. It's the inverse of exponentials. You know, in math, a lot of things have inverses. So, like adding and subtracting are inverses, multiplying and dividing, squaring and square rooting. The same thing goes with exponentials and logarithms. They kind of undo each other, as you'll see. So, you've seen exponential equations before. They're where you have a variable as an exponent. Sometimes it's not that hard to solve these things. So, if I want to solve for x here, like 5 to the what power will give me 25? It's just 2. On this one, how could I get these two sides to equal each other? Well, all I would really have to do in this one is just do 3x minus 2 equals x, and then I could solve for x that way. But on a problem like this, how do I solve for x? Because like 5 to the what power is going to give me 7. I know 5 to the first power is 5 and 5 to the second power is 25. So x is going to be like 1 point something. But what exactly is it? And how do I solve for that variable there? Like I can't just divide by 5 because this is not multiplication. It's to the power of 5. So that's why we need logarithms. So before we get to actually solving, you need to know what logarithms are. So here's how they work. We usually write the word log, shortened for logarithm. And so if logarithms have what's called a base, which is this number written kind of as subscript. And so this we would say log base 2 of 8, or the base 2 log of 8, something like that. If I want to see what that is, this is basically asking, if I take 2, like how many 2's do I need to multiply together to give me 8? And so that would be 3 of them. That's all a logarithm is it's saying how many of these numbers do we need to multiply together to get this number. In this case, it would be 3. You may notice that's very similar to how exponents work. The whole point of exponents are like repeated multiplication. So these two are very related. If I write it as a logarithm, we have the base here, and then you need 3 of them to give you 8, which is basically the same thing as saying 2 to the third power is 8. These two statements are equivalent to each other. This one's just kind of written as a log, this one's written as an exponent. So you need to be able to go between the two. For example, this would be asking 4 to what power gives me 16? Like how many 4's multiplied together give me 16? It's basically like saying 4 to what power gives me 16? And clearly that would be 2, because 4 squared is 16. So this evaluates to 2. All right, so kind of the little trick here that I use to help remember this is, if you want to rewrite a log as an exponential, all you have to do is you start with a base, and then you do a little swirl here. So the swirl is kind of helpful. So you do the base to that power equals x. So the base to the y power equals x. The base to the y power equals x. You can go back and forth as well. So for example, this right here is, first of all, the word evaluate just means like, what is it? What does it equal? What does it spit out? This is asking 2 to what power gives you 16. It's the equivalent of saying 2, like if I want to see what it equals, it's like saying 2 to the x power equals 16. And that would be 2 times 2 times 2 times 2, 4 times. So x is 4. On this one, I'm trying to see what it equals. And so 5 to what power gives me 1? That one's a little weird. 5 to what power gives me a 1? Well, if I try to put a 1 here, that would just be 5. So I'm going to actually have to do 0. Because anything to the 0 power is 1. On this one, we're doing 3 to what power gives me 27? That would be 3, because 3 cubed is 27. This one is 5 to what power gives me 5? That would just be a 1. Oops, sorry, I answered it. Same thing here, 6 to what power gives you 6? Again, it would just be a 1. 14 to what power gives you 14? Again, just a 1. So you may notice any log where the base and this number here match is always going to be a 1. And what about this one? Notice on this one, there actually is not a base written. It just says log of 100. If there's not a base written, it's understood to be a 10. Log base 10 is very useful, especially in fields like engineering. Engineers use this all the time. But so if anything is not written there, it's understood to be base 10. So this is asking 10 to what power gives you 100, which would be 2. All right, so a couple things here. First of all, you are not going to be able to do these in the TI-84 or your phone calculator. If you have a fancier TI calculator, like one of the real fancy ones, you actually can do different bases. But in the TI-84 and in your phone calculator, you can only do just plain old log. And there's actually one other one you can do. Let me show you this. So there are two kind of special logarithms. One is the one we just talked about. If nothing is written, it's understood to be base 10. We use that one quite a bit. Also, there's one that's called natural log. We write LN for natural log. When I write it, I usually write a cursive LN so that it doesn't look like a 1, but LN. This stands for log with a base E. E is actually a number. It's like pi gets its own letter. It's about 2.718 and so on. It is in your calculator, but E is a number that pops up a lot with exponential stuff. And so if you ever have log with a base of 2.178, whatever, E, we call that natural log. So these two buttons are in your calculator. There's a log button and there's a natural log button. But you can't do any other bases. There are ways to get around it, but you can't, there's no specific button in the TI-84 or a phone calculator for anything except for these two. All right, let me show you how natural log works a little bit. So, this is the natural log of E. Remember, this is really like saying log with a base of E, and then I'm putting E into the function. So, E to what power would give you E? That would just be 1. Or let's try this one. This would be log base E, because again, natural log is log with a base of E, and then it's got E squared in it. This is like saying E to what power would give you E squared? Well, it would be 2. E to the second power would give you E squared. Same thing here, log base E of E cubed. E to the what power would give you E cubed? And it would be 3. So you may be noticing a pattern here. Basically, natural log and E cancel each other out, and you just get whatever's left in the exponent. So like natural log and E are really just going to cancel each other out, and you're just left with 50. That always happens. If you want to go ahead and try it, you can actually put these in the calculator. So try natural log of e and see what you get. We're not quite to this yet, but I do want to show you it can cancel out another way as well, which is like if you do e to the power of the natural log of something, those also cancel out. So feel free to try these in your calculator as well, but these will still just cancel out and give us a 1. This will still cancel out and give us 2 or 3 or 50. So pretty handy. All right, these are actually going to be really easy now that we know how these logarithms work. So remember kind of that swirl pattern. So if I want to solve for x, I know that 2 to the 6th power is supposed to give me x. So all I have to do is 2 to the 6th, which would be 2 times 2 times 2 times 2 times 2 times 2. That's 4 times 2 is 8, times 2 is 16, times 2 is 32, so 64. This one is just 4 to the 2nd power equals x, so 4 squared, which is 16. This one is 4 to the 0 power equals x. 4 to the 0 power is just a 1. And this one, just as a refresher, natural log means log base e. So these two are the same. Just by the way, whatever is in the function here, you can write it in parentheses, but you don't have to. See how these didn't, but this one did? It really doesn't matter if you put parentheses or not. Okay, so this is e to the 5th power equals x. So the answer is just e to the 5th. You could get out a decimal if you wanted. Let's try a few more. So again, just kind of use that swirl. 5 to the 2nd power equals this. And it equals this whole thing. So 5 to the 2nd power equals x plus 1. So 25 equals x plus 1. So x equals 24. Just subtract 1 from both sides. On this one, before you start doing any sort of swirl, you need to actually deal with the 3. Order of operations applies here, and I need to get rid of that 3 first. So just like you normally do when you're solving, just divide both sides by 3. That leaves log of x plus 4 equals 2. You do need parentheses here so that I know the whole thing is in the logarithm, not just the x. All right. Remember, if there's nothing written, it's understood to be base 10. So this is going to be 10 squared equals that. So 100 equals x plus 4, subtract 4 from both sides, and you get 96. There we go. On this one, again, I need to kind of get the logarithm by itself before I start trying to do the swirl. So I'm going to start by adding 2 to both sides, because that's not included in the logarithm. All right. Remember that natural log is really log base e. So this is e to the 9th power equals 3x. I could put e to the 9th in my calculator, but I'm just going to leave it as e to the 9th. And then we'll divide by 3, and that's the answer. All right, I just want to show you what happens if there are logarithms on both sides of the equation. If they have different bases, you're kind of out of luck. But if they have the same base, I mean, just use your common sense on these. So, like, what does x need to be to make these two things equal to each other, to make them the same? It's kind of like one of those spot the difference pictures. All I need is for x to be 12, and then literally they're identical to each other. So x is 12. Same thing here. It's pretty much like you're just ignoring the log 3. It's just like, all right, well, those parts are already the same, so now I just need these parts to be the same. So you do 5x minus 1 equals x plus 7. And then subtract x from both sides. Add 1 to both sides. And then divide by 4. Same thing here, they're both natural logs, so all I need is for this piece to match this piece. So I'll just do 4x plus 1 equals 2x plus 5. Subtract 2x from both sides, and then subtract 1 from both sides. Again, it's 2. All right. I do want to clarify, it seems almost like we're dividing by log on both sides, and we're not really. It's just that we're trying to get the two sides identical to each other. Also, log does not exist by itself. Like, I can't just have my answer be like log. It's like square root. It's an operation. It has to latch on to something like a parasite. It can't exist by itself. So you can't just have log or log base 5 or something. It's got to have something inside it. All right, so just to refresh on all that, if you want to rewrite a logarithm as an exponent, just take the base to this power and it has to equal that number that's in the logarithm. Also, there's a couple special logs. Log base 10 is the one where we don't write it usually, and natural log, which is log base e, which is that special number there. It's actually called Euler's number. It has a cool history. All right, in the next video we'll get into some log properties.